Hi, welcome to our poster presentation. Genomic database sharing is critical to biomedical research, clinical practice, and customized healthcare. However, the sharing of a genomic database is usually not viable due to the copyright and intellectual property concerns from the database owner. In other words, the requirement of copyright protection and anti-piracy may prevent the database owners from sharing their genomic database. The steganography technique of database fingerprinting can be used to claim the copyright of the database owner, prevent illegal redistribution of the database, and identify the source of data breaches. Here is the model of the genomic database fingerprinting system where the database owner wants to share its genomic dataset to different service providers. And when sharing the copy to different service provider, he will insert the fingerprint at different locations of the dataset. So if there is a malicious user that leaks his dataset, then the database owner can still accuse him for the data leakage. The inserted fingerprint will change the SNP value at different locations of the genomic database. And the fingerprint is customized for each service provider. In particular, it is the hash value of the concatenation of the private key of the database owner and the serial number of the service provider. For example, when sharing the original genomic database to the service provider IJK using their different fingerprint bits, it will lead to different locations being modified of the original database, and the modified locations are represented in the yellow dots. To be more specific, let RIP be the piece SNP of individual I in the genomic database, and FL is the else bit of the fingerprint bit string. Let X be a random binary bit, and M is the result of the exclusive OR operation between X and FL. So the fingerprint insertion is completed by setting the teeth to the last bit of IIP to our mark bit M. And in the fingerprinting scheme, the collection of I, P, L, and X are all randomly generated. And the random seed is set to be the concatenation of the private key of the database owner and the primary key of the data record. Please refer to the paper for the detailed procedure of fingerprinting insertion. And the fingerprinting extraction is the reverse process of the insertion procedure. Genomic data has very rich correlation as shown in the figure on the right. In the paper, we use S to represent the row-wise correlation between genomic data, and in particular, it can be caused by the Mendel's law and the similarities of genomes from family members. And we use J to represent the column-wise correlations in the genomic data. In the paper, we characterize J as a pairwise joint distribution between the genomic data points at different locations. Since the previously mentioned vanilla fingerprinting scheme randomly changes the entries of the genomic database, it will compromise both row-wise and column-wise correlations and cause a significant statistical utility loss in the resulted fingerprinted database. As a result, the attacker can take advantage of the correlations to infer and distort the inserted fingerprint and compromise the vanilla scheme. To make the vanilla scheme be robust against the correlation attacks that take advantage of the row-wise and column-wise correlation among genomic data, we developed the corresponding mitigation technique. And this technique can serve as post-processing steps for the vanilla scheme to mitigate against the row-wise and column-wise correlation attack. In particular, the row-wise mitigation technique modifies the SNP tuples that violating the Mendel's law, and at the same time reduce the discrepancy of SNP similarities that are caused by the vanilla fingerprinting insertion. And similarly, the column-wise mitigation technique also reduces the discrepancy of SNP joint distributions caused by the inserting of vanilla fingerprint. The row-wise mitigation technique contains two phases. In the first phase, it modifies SNP tuples that violate Mendel's law. Here is an example of violation incident where the mother's SNP has been fingerprinted, and to make this tuple satisfy Mendel's law, we update the child's SNP from 0 to 1. The second phase solves an optimization problem to reduce the discrepancy of the SNP similarities. The design idea of the column-wise mitigation technique is try to modify unfingerprinted entries in the fingerprinted database such that after the modification, the marginal distribution of the SNP at a specific location is close to the reference marginal distribution at that location. And the modification plan is obtained by solving this optimization problem, which essentially performs the mass transport between two distributions. And the optimal transportation plan is used to move the mass from one marginal distribution to another. In the experiment, we consider a genomic database contains 1,500 individuals, among which there are 150 family members. We evaluate the fingerprint robustness against a random bit flipping attack and correlation attacks. We use the accuracy and consistency of top 50 SNP that has strong association with a phenotype before and after fingerprints as the utility metric. We say attack is successful if it can compromise more than half of the fingerprint bits. And to the advantage of the attacker, we let it has the ground truth knowledge of the row-wise and column-wise correlation. Here is some of the experimental result, and the takeaway message is that the random bit flipping attack is not as powerful as the correlation attack, which can easily compromise half of the fingerprint bits. However, when applied our proposed mitigation technique, the correlation attack can hardly compromise more than half the fingerprint bits. And on the bottom, we show that our mitigation technique can still preserve high utility of the databases.